Yeah, welcome Haberdashers Boys School. So we'll get started in a minute. You're gonna have 15 minutes to present. I'll give you a 5-minute warning, 2 minutes, and 1 minute. Just peek over at me occasionally because I know you'll be focused your attention out there. And then afterwards, we'll have 5 minutes of questions. You can get started whenever you're ready. Just if we ask that you begin by everyone introducing themselves, and then I'll start your 15-minute timer.
I'm Oliver.
Dawei Tao, famously known as Tupai.
And I'm Arian, and we're team 17705 from Haberdashers Boys School from the UK, and here's our solution to the hot button issue. I'll now hand over to Oliver.
So in question 1, we were modeling the temperature inside a building during a heat wave. We chose the city of Birmingham in the UK, not in Alabama. We start with some simplifying assumptions. So most importantly, we assume the temperature in a building everywhere is constant. Otherwise, the model becomes pretty complicated. We also ignore humidity and wind speed, since these affect perceived temperature more than actual temperature. Now, when looking at factors, we decided outdoor temperature is the primary factor that influences indoor temperature. And so as avid physics students, we decided to go for a differential equation model based on Fourier's law of heat conduction. We also recognize that indoor appliances can lose energy due to inefficiencies. And this becomes an extra term in our differential equation, which looks like this.
So you can see the differential equation here and our table of variables. The first step in solving it is to put Q equals mct. And this is it's a partial first order differential equation. And using the method of integrating factors, we can solve it analytically, which is superior to a numerical solution for a range of reasons. And here's the solution we obtain. You can see we've got a constant K there, which is shorthand, and T0, which is our indoor temperature at the start of the day. So in addition to all of that, we also need some values for our constants and also some functions of time. So specific heat capacity of air is just a constant, so that's nice and easy. Mass of air inside the building, that's the square footage of the building multiplied by the height of the average room multiplied by the density of air. That's not so bad. For T0, temperature at the start of the day, we took room temperature for that, but you'll later see when we varied that in the sensitivity analysis, it almost has no impact at all, so it's not that important. But thermal transmittance, so we looked at the construction date of all the houses given, and that allows us to deduce a likely wall type, and then we get our value. The wall area, we did a little bit of research, a little bit of random sampling here to find the quantities R and H, and then it's quite easy from there to find an equation for the total wall area. And then I of T, the power transfer due to inefficiencies in indoor appliances. So we profile the houses as high, medium, or low energy use. And this is according to the UK energy regulator. And then we break down this energy use. Again, this is averaged across the entire UK. And for each of these energy uses, we assign an efficiency. And we also assign a time of day when these are likely to be used. And summing over all of these, we obtain a plot of I of T.
Now, the temperature data provided by M3 is in discrete hour intervals, but our model wants a continuous function as input. So we fit a continuous curve to the data using a truncated Fourier series, here consisting of 4 sine waves. And we fit this via gradient descent in the Desmos graphing calculator. So we initialize our fit with some random parameters here. Some we choose manually just to speed up training. And then each iteration, which was achieved using an action, we update each parameter by their gradients. Over time, the loss decreases and we get an increasingly good fit, which looks like this at the end. And this can now be plugged into our model. Also, shade can have an impact on the outdoor temperature. So in the data provided, each house was assigned a shade descriptor of either not at all shady, not very shady, somewhat shady. For each of these, we assign them a temperature drop, and then throughout the day, we scale that temperature drop by this kernel here to account for sunrise, sunset, etc.
And here's just an excerpt from our code. You can see our parameters there for each house, and I'll just draw your attention, not sure if you can see it, but at the bottom, we have the integration. That's using SciPy's function which implements the Simpson rule. And this is verbatim exactly the equation that you saw earlier in the presentation. So here are our results for each of the 4 houses. Now, the first thing we thought when we saw this is, wow, that's a lot of degrees. But if you look carefully, you'll notice there's actually this letter F here. Apparently there's this thing called Fahrenheit. Anyway, after digging our equation books out, we managed to convert to Celsius, and it turns out, yes, it actually is a lot of degrees. We'll come on to why the values are so high later. But first, sensitivity analysis. So we varied T0, as mentioned earlier, and had no impact. We varied I of T, and this did have a significant impact, which is to be expected, given that this is it's a key contributor to the model. So we'd expect that. And then some brief advantages, disadvantages, strong, flexible, high stability, all good things. The main disadvantage is this very high temperature value. Why is the temperature value so high? Well, the main thing we think is likely to be the cause of this is I of T being unrealistically high. And the good news is that because our model is so flexible, we could revise I of T, put in new I of T, and we'd get more reasonable results. I'll hand over now to Raj and Dev for question 2.
So now we'll present our solution to question 2, Power Hungry, where we modeled the peak electricity demands of Birmingham during the summer months. So just first, some assumptions that we made. We assumed that Birmingham's monthly electricity consumption and the UK's monthly electricity consumption would follow the same distribution. And we also assumed that trends in any complicating factors would remain steady. So just a brief overview of our model. Our model had 3 parts to it. Due to the poor availability of data for Birmingham's monthly electricity consumption compared to the UK's as a whole, which was much greater, we decided to model, the bulk of our model was designated to modeling the UK's national electricity consumption, with another model for Birmingham's contribution to this, and then finally a third model to correct the residuals of the previous models and better capture those spikes. So here you can see some of the variables that we took into account and just units for them. So starting off with our first model, which was used for modeling Birmingham's contribution, we just first started with an initial investigation, plotting the whole of the UK's and Birmingham's annual electricity consumption. And the trend was entirely non-obvious, so we also plotted Birmingham's contribution. And at first, it looks really erratic, but you may have noticed that the scale of the graph is quite misleading, and there isn't actually a very high range, so it is about constant. But anyway, we decided to go ahead and try 3 different models for this, and we eventually settled on the quadratic model because it has the minimal mean squared error. We fit these models using gradient descent in Python's sklearn, and one disadvantage of this, though, was that because it's a quadratic model, as t approaches infinity, it will just tend to negative infinity.
So now I'm going to be talking about model 2, which is kind of the bulk of the model. So if you see our plot on the left here, it's pretty clearly seasonal, as expected. And so therefore, after some research, we settled on a Holt-Winters model, which was implemented in Python's stats models. So a Holt-Winters has 3 components, the level component, the trend, and the seasonal. And so there are 2 parameters, additive or multiplicative, in terms of the trend and seasonal components. And because there were only a small number of combinations, we just decided to test all of them. And so we ended up having 2 multiplicative components with the least mean squared error, and this is the model that we fit. The equations there on the left, you'll see that L sub t is level, the B sub t is trend, and the S sub t is seasonal. And so we were pretty impressed by this. It looks pretty good. But there is one hair in the soup, and it's these little blue spikes. And so when you want peak electricity demand, you always want to err on the side of caution. And so we wanted to kind of capture these spikes a little bit better. And so that leads me on to model 3. But first, I'm going to talk a little bit about our technical implementation of the code. And so here you can just see we loop over all possible combinations of additive and multiplicative, and we find the one with the least mean squared error. And so here's model 3. To make sure we weren't having some kind of delusion, we wanted some kind of objective metric to determine how much we were misrepresenting these spikes. And so after some research, we settled on a forecast bias. Here we called it a peak demand bias. And we just examine the most extreme values and see how they compare to the rest of the data. And so we had a systematic underestimation. And here's just the calculation for that. And you can see at the top that it's just the top 10%. So here's the model 3. Well, first we plot the data. It looks pretty random. It looks pretty meaningless. But if you ignore the scale of the amplitudes of the graph, you can see it's kind of on the time scale of about 6 months is the period, which coincides with the seasons, and therefore that leads me onto our first option for model 3. Linear regression with Fourier terms to better capture seasonality. And this T here is average maximum temperature, which we've normalized. And we decided to raise it to some powers to kind of emphasize those extreme values. The justification for this is as follows. We think that when you have more extreme temperatures, you're going to be more likely to use things like air conditioning and heating, and these are pretty big users of electricity. These are use a lot of power. As you can see then on the left, our eventual combined model, which we think looks pretty good. And here's our second model in just a sec, but here's just the implementation for that. You can see this function down below just loops over a certain number. Like we can just select the number of terms, and then we looped over up to a large number of terms and found the one with the least mean squared error. So here's our second option for model 3. We just followed standard advice on selecting parameters for a seasonal ARIMA model. And so you can see here the autocorrelation function plots and the partial autocorrelation function plots. And so here was this model, the fit. You can kind of see it's a bit similar. The graphs aren't huge, but you'll see also it kind of moves away from how it originally used to match. And so you'll see that captured in the figures here. The mean squared error for the SARIMA is actually significantly worse than the regression, and the peak demand bias didn't even really improve. And so unanimously, we picked the regression model. And so here are our results. You'll notice one little thing. Earlier, I talked about temperature influencing the results a lot, but quite curiously, in the summer months, the consumption actually goes down. And the reason for this is that in the UK, we don't really have air conditioners. Very few homes have air conditioning. And so a lot of, I know Americans find it funny when we call 15 degrees Celsius hot or 20 degrees Celsius hot, but our homes are built to capture heat. 20 degrees Celsius is proper shorts weather, lounge on the lawn, get a suntan weather. So yeah, that's why it's actually decreased. And now onto the sensitivity analysis. We decided to only do this on the second model because it was just the most important. And you'll see it's pretty stable on the small variations of parameters.
Yeah, so I'll just be going through the evaluation now. We thought our main disadvantage was the fact that this isn't feasible in the long term because of Model 1, as I mentioned, but our main advantage was its modularity, so it is actually quite flexible. We can fix the whole model with little effort by adjusting our first model, and then it should still be feasible in the long term. Now I'll be handing over to Dewey and Orion for question 3.
So question 3 was about calculating a vulnerability score to power outages and heat waves for neighborhoods in Birmingham. So the assumptions. The assumptions were mostly made due to insufficient data and to avoid overcomplication. I'll gloss over that. Our rationale. So we had two potential approaches. The first approach was to use a normalization function, so to put each factor through a normalization function and then sum them up. We decided that this would be just difficult to justify which normalization function to use. So we considered using approach 2, which was ranking each factor and summing the total ranks. And the advantage of this is that it's more versatile when comparing the neighborhoods in Birmingham. Sorry. I also would like to say that it would have been great to consider, we really wanted to use k-means clustering, but if we had more time and more data, that would be much more.
So here are the 5 factors which we considered, 2 for power outages and 3 for heat waves. These factors we won't consider because they're difficult to quantify and data is incomplete. So for energy consumption, we could look at the total consumption, but we decided looking at each individual's electricity usage is a better indicator of how dependent they are on electricity. So this is calculated by dividing that by the population. And then for vulnerable jobs, we look at the proportion of jobs that are in vulnerable industries. So we just sum up the number of jobs in those, divide that by the total number of jobs to obtain this ratio. Now I'll hand over to Oliver and Raj.
Okay, so on to the heatwave related stuff. So first we have the work and education risk. So we split jobs here into high risk, medium risk, and low risk with respect to heat waves. And we weight them 100, 10, 1 logarithmically. There's some justification there. Then for transit-related risk, we wanted to encapsulate the density of individuals on transport because the denser, the warmer, and the warmer, the higher the risk of heat stroke, etc. And this ratio here, you can see N and S, how they're defined, encapsulates that.
And now onto leisure-related risk. So here we just kind of have 3 factors. Basically, how much green space is there for you to cool off? How much space is there for designated areas for you to cool off? And how close are you to get drinking water? And then we don't have really any feasible way to compare how important these are, and so we just take the default position of weighting them equally.
And then finally, we also wanted to encapsulate the fact that higher temperature means higher risk everywhere. So we got a lot of data for excess deaths and temperature during heat waves in summers, and we did a quadratic fit. By quadratic, well, it makes sense that if you're already at a high temperature, the same increase in temperature will be even worse than if you'd started low. You can see the fit has a very low R-squared. It's important to understand that when you're putting in the temperature, you're not actually calculating excess deaths. You're just calculating a multiplier that represents the increased risk. We multiply through our raw values by these.
I want to ask a high-level question, because you noticed something interesting in the data, which was that in the US, like in the summer months, the electricity use goes up, and it seems like that's not the case from Birmingham. And I think you attributed that to the lack of air conditioners. So taking a step back from like all the modeling you did, is Birmingham at risk for heat waves? Is it a problem we should be worried about? Is the fact that there are no ACs telling us that it's not an issue, or is it saying maybe it's less prepared? What was your takeaway from the modeling you did?
Yeah, Birmingham in particular has quite a lot of office blocks, and it is really at risk of heat waves because like it kind of functions as an urban heat island. Everything basically traps heat, and there's no way to get rid of it. And as like kind of climate change gets worse and temperatures increase, even just slightly, it gets even worse. And air conditioning, especially in the older buildings in Birmingham, can't really be installed. And Birmingham's not a very wealthy area in general, and so air conditioning is unlikely to kind of make a presence there. So yeah, it is really at risk of heat waves in particular.
Okay, great, thanks.
Can I just add?
Yeah, go for it.
Based on British weather, I wouldn't say it's as at risk as, say, Memphis in the US, but as a very urban city like London, definitely still has risk.
Thanks.
Okay, in number 2, you did a lot of modeling, a lot of coding, but could you comment on the average energy consumption in the future, like for the next 20 years? Any thoughts about that?
Yeah, so we didn't have a specific figure for that because of the first part of our model was very short term, and I guess we could have used a linear regression to like kind of assume that it does continue linearly and forecast into the long term. But I would say the trend is that it was decreasing pretty significantly if you looked at the plot, that the trend was decreasing. And this is likely to continue, but we can't really say with huge amounts of certainty because of things like innovation, also political changes like environmental initiatives.
Thank you, makes sense.
I have a question about your question 1. You acknowledged that the air temperature that you're predicting within the dwellings is higher than most. In your talk here, you focused on the IFT term. And I was wondering, why did you focus on that, and what would you adjust?
Well, of the 2 terms we had, which were the heat conduction stuff and the IoT, the heat conduction is the one with the very strong, theoretical physical foundation. And there's no reason to believe that there would be anything wrong there. And in some simulations we did where before we had added the IFT term, we found that the numbers were all very reasonable. For IFT being wrong, it's hard to say. Part of it could also be due to underestimation of the efficiencies of devices. So obviously, nowadays, efficiency is only increasing. And so it may be the case that we're overestimating heat loss there.
So I have one technical question, but I forgot. I wanted to comment. I have never seen gradient descent run in Desmos. I use Desmos for a lot of things, but that is new to me, so kudos on that.
Thank you.
For question 2, you use this Holtz-Winter's model, which it actually captures some seasonal effects, right? It can capture cyclicity in the data. And then I think you nicely observed that there were some errors in the model, some spiking errors, and you tried to account for that. But when you did that second accounting, you actually attributed those additional errors to seasonality. I didn't quite understand the story there, right? It felt like the original model should capture seasonality, and if the original model wasn't matching the data, there should be some other reason why. So can you explain that choice to correct those errors with another model that was trying to capture seasonality?
Yeah, both. I mean, both of them kind of. It wasn't to correct any seasonality effect. It was just because the first model, obviously, because it will predict expected value. So it will systematically kind of always be away from any spikes, and so that's. I mean, necessarily the other model had to be seasonal, otherwise it would kind of just flatten out the seasonality into basically just like to make it more uniform. So I guess the second one kind of had to be seasonal as well.
So could you have, like, why, for example, use two different seasonality? Like, you used, I think, a model with some fixed Fourier frequencies for your correction model and use this Holtz-Winters for the first one. So why, like, could you have just corrected with the Holtz-Winters model?
Yeah, we did actually try another Holt-Winters model, but it was just making it worse by like a lot.
Okay. Okay, makes sense.
So because you're a Haberdashers boys school, I have to ask about your outfit. What do the numbers on the back represent, or is it random?
Should we do a live demonstration?
Yes, do a live demonstration.
All right, so let's see this. Okay, wait, can you look through there? Thank you. I'm glad I asked then.
Okay, thanks. If you guys want to say a word of thanks to whoever, now's the time to do it.
So, firstly, I'd like to thank our coach, Miss Harrison, and our chaperone, Mr. Broadwith, for their endless cheese jokes, public dances. It was great fun. I want to thank the twins' parents and Oliver's mum for giving us a place to stay for 14 hours and sheltering us from the harsh British weather. And finally, thank you to all those running this competition at M3, Siam, and Jane Street. And it's a wonderful opportunity. We really enjoyed New York, and thank you very much.
I just want to add one quick shout out to Mr. James Lee watching us from home. Thank you for your support, sir.
We have a 10-minute break now, I guess, or a little bit more than 10 minutes till 11 o'clock, but we'll meet back here at sharp at 11 o'clock.